Hello, my name is Thomas Hillen and I would like to talk to you today about quadratic functions. Many of you know what quadratic functions are, and I've given you a general form here. F of x is ax squared plus bx plus c, where a, b, c are constants. And to make it a quadratic, we need the quadratic term, which is the first term here with the x squared. So we need to require that a is non-zero, because otherwise, if a would be 0, we would have a linear function. A linear function is a different topic. Now, I focus so much on quadratic functions because they will be the workhorses through the calculus course, and we will use them all the time. And it's just good if you are able to look at a quadratic function, at a formula like this, and then know already how does it look like. Another form which often arises is the function form here with the function g, which is d times x minus e times x minus f, where d, e, and f are constants, and similar as above, we assume that d is non-zero. So we have a quadratic. Now here this red one is a function f, which I have plotted using Maple. And of course you know they all look like parabolas. So this is a parabola which is shifted a little bit below the axis. It has two zeros. 1 0 is sitting here, 1 0 is sitting here. So we will talk about all these issues as we go through these slides. So how do parabolas or how do quadratic functions look like? Well, the most famous is, of course, the parabola f of x is x squared, and it looks like this. It touches at 0, it is symmetric, and has about this form. If I do the opposite, minus x squared, I get just the whole function turned upside down and put to the negative part of the plane. And in fact, this is how all parabolas look like, more or less. So we only have two types. We have parabolas of this shape, and we have parabolas of this shape. And they can sit in the coordinate system wherever they want. So they can sit above the axis, below the axis, they can cross, they cannot cross. In any case, so this we call concave up, and the other case is called concave down. And now I'm interested to differentiate when does concave up happen or when is a function concave down. And the idea to understand this is the leading order term of the quadratic function. So this is the leading order term, this a times x squared. And if a is positive, you have concave up. So how to see that? Well, if you plot a coordinate system x here, and if you look for very large numbers of x, then this x squared term will be even bigger. And so this term eventually dominates whatever the other terms are. And so for very, very large x, this gives you the sign of the function. And if a is positive, the function is positive. And similar in concave down, if a is negative, the function is negative. So this case happens when a is positive, and this happens when a is negative. So let's do some examples. Here I have 3 examples for you. The first function is 2 minus x squared. So clearly the leading order term is negative, right? It is a minus 1. That is the factor a in front of x squared. So this must be concave down, sad face. The next function has a 3x squared plus 5x. So here the leading order term is 3, and so you have concave up. It looks like this. The last one looks a little bit more tricky. So we really need to multiply to see what the square term is. So let's multiply this out. X times 2 is 2x. X times minus x is minus x squared. Here is the square term. Minus 2 times 2 is minus 4. Minus 2 times minus x is plus 2x. So for now, only of interest is this term, where we again have a minus 1 as leading order term. So we get an upside down parabola, or what I called concave down. So that's already cool. So you don't have to do much. You just need to look at the leading order term, and you know already which way the parabola goes. So next we look at the zeros of a function, and the zeros are defined to be values of x so that the function is equal to 0. Now a quadratic function can only have 0, 1, or 2 zeros. And to show you 3 typical examples, so it maybe looks like this, or it can look like this, where it just touches and has 1 0, or it crosses the x-axis twice and has 2 zeros. Now in the special case where f has this specific form, dx minus e times x minus f, we see immediately what the zeros are, because, for example here, if you sub in the value e at this location, then you get e minus e, which is 0. So 1, 0 is already given by x is equal to e. And the other one is, of course, given by x is equal to f. So if a quadratic function has this form, then the zeros are given by e and f. Now I just noticed that I use f twice on the left and on the right, so this is completely impossible. So this should be a capital F to distinguish the zero f and the function f. So I apologize for that. If we do not know what the zeros are directly, we can use substitute test values. So for example, we can just substitute a 0, 0, and then see what happens. Or we substitute 1 or -2 or whatever number we fancy. So let me show you how this works at another 3 examples. Functions m, n, and l. So let's start with m. M is clearly concave up because the leading order term is a 3. But then I sub in some values. So m at 0, for example, is 0. Hey, yippee! We have another 0. So that's indicated here. I can sub in the value 1. So m at 1 would be 3 plus 2 is 5. So then we have a 1 here and a 5 here. So this is our value. And I should also substitute some negative numbers because I want to know what happens in this area here. Does it continue like this or whatever? And it turns out a good value to try is -1/2. Of course I tried -1, but it didn't give me any useful information. So I try m is -1/2. So we get 3 times 1/4, which is 3/4. And then we get 2 times -1/2, which is -1. So together this is -1/4. And which is negative. So then here we have -1/2 and here we have -1/4. So this is our third point. Now we have enough information to plot the parabola because it only can look like this. Right? So it has 2 zeros, it goes in the negative region here. Now the function n, again, let's look at the leading order term. So we have 2x minus x, which is -2x squared. So it is concave down. If we sub in 0, then we get 0. And if we sub in 1, for example, we get 1 minus 1 is also 0. So we have 2 zeros and we have concave down. So we are done. So these are the 2 zeros and the function must look like this. Finally, the last function, L is certainly concave up. And then if I sub in 0, I get 1. And if I sub in any other number, I'm bigger than 1 if x is non-zero, because the x squared is always positive, so I'm always adding something to 1. So this function has no 0, and it looks like this, where this minimum point is exactly where 1 is. So let's summarize. To understand quadratic functions, you do 3 things. So first you look at the leading order term, then you know already if it's concave up or concave down. Then you look at the zeros if you can find them. If you cannot find them, you substitute certain values, see if they are above or below the x-axis, and then you find the qualitative shape of your parabola. And then you are done.